All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Maria Laura Delle Monache, who is an assistant professor in the Department of Civil and Environmental Engineering at the University of California, Berkeley. So thank you for having an early talk. So Maria Laura, something about Maria Laura, she received her PhD degree in applied math from the University of Nice, Sophia Antipolis in France. And before joining UC Berkeley, she was first a postdoc at the Rutgers University in the US, and later a research scientist at INRIAG Grenoble in France. She, as you have seen, she has won many awards in her career so far. Her research is very exciting because she mixes formal mathematical frameworks with very applied control strategies for mixed autonomy traffic. So, and I really like the mix of the theoretical soundness and the actual impactful results she showcases. Today, she's going to present a talk titled Control Strategies for Mixed Autonomy Traffic, which is a very exciting project she has been working on for the past few years. And I look forward to hearing more about it. And I'm very excited to give you the stage, Maria Laura.
Thank you, Joel, for the invitation and also for the very kind introduction. So today I wanted to talk to you about a bit mixed autonomy, and in particular mixed autonomy focused on traffic application. And we're gonna go a bit onto the journey that's been also my career in a way. So we'll start with try and bit understand what type of problem we will look into the talk, but then we'll dive into some mathematical theory and control theory that is something that for traffic flow application, it's very, very interesting. So it creates a lot of control and mathematical problems that allow us to build new theory for different types of system, both in the more formal setting in terms of equation, but also in terms of data-driven methods. And then if there are times allow, we'll go a bit more into the detail on how to transfer what we'll see in theory then into real-world application. Okay, so the first time when we started looking at the traffic flow application, the first problem that we started to look at was stop-and-go waves. And here you see an example here on the top video of a typical stop-and-go wave phenomenon. This was taken with a drone by Feng Yu, this video here. And you'll see what happens. So here you can see a stretch of freeway, and there's no particular physical reason for this type of behavior to happen. There's no obstacle, there's no lane closure, there's no work zone. It's completely a freeway. And it has been shown that stop-and-go waves in general happen because you have human drivers that tend to get distracted. It happens to everybody when we're driving. We're suddenly, I don't know, receive a text, look at the radio, or nowadays probably an app that streams music, and suddenly we're not paying attention anymore to what's happening in the road. And so we feel uncomfortable with the current traffic conditions, slightly tap on the brake, and that propagates basically backwards and creates this type of phenomenon that you see at the top here. So stop-and-go waves are bad for a variety of reasons. First of all, they are bad from if you are a traffic manager managing that freeway, because you have queue for no physical reason, so there's no reason for it to be a queue. They are bad from an environmental perspective, because especially when you have internal combustion engine, this type of behavior, acceleration and deceleration, is what causes the highest fuel consumption, and so the highest pollution. And it's also pretty annoying, let's say, if you are the one that it's driving in those traffic conditions. And so we wanted to see if there is a way to get rid of the stop-and-go waves. And so this is the phenomenon that started for us all of this thought about traffic flow and how to use mixed autonomy in the context of traffic flow. So when we think of stop-and-go wave from a physical phenomenon, the characteristics are essentially we have a very high oscillation in terms of speed. So you see, as you can see also on the video, so the cars accelerate and brake constantly, and that creates basically a high oscillatory behavior in all the vehicles that are in that stretch of freeway. And then also it creates basically shocks, which are basically these traffic jams that propagates backwards into the freeway. And you can see how the shock wave then propagates also when we look at the different car trajectory in time and position. And so when we started looking at this type of problem, and we kind of thought that the human behavior is the one that causes this, so then what if we can replace some of those vehicles with vehicles that can do some intelligent control, or something that can break the pattern and break the cycle here and create a better behavior for traffic. And so a few years back, together with a group of researchers from currently at Vanderbilt, so Professor Work and Professor Professor Sprinkle, and then also with Professors Seibel, then Berkeley. So we went to Arizona and decided to try this assumption. So let's replace one of the vehicles with an autonomous vehicles and see if we were able to break the stop and go waves. So at the beginning of this video, you've seen the black arrow on the AV. So at the beginning, you see that basically we were trying to reproduce what you saw on the freeway on a ring road. So that stop and go wave phenomenon. And then we had the AV act as basically as a smart controller. And you'll see that once autonomy kicks into this circle, you're gonna see that the AV is able to basically reduce the stop and go waves. And here you can see the AV, and if you see here you can see the trajectories. So at the beginning, you see the same phenomenon we've seen before, with creation of shocks, and then after a bit, we'll see that basically all those shocks have gone away. And you can see it even more clearly if we look at the velocity versus time. You're gonna see at the beginning you have all these waves, and then after a bit, these waves dissipates once the vehicle starts acting in a smart way. And this allowed us to prove basically that we can reduce the standard deviation of the velocity, the braking events, the fuel consumption, 42%. And what was for us very amazing and good also from a transportation perspective is that we were able to also improve the flow. That means improving the throughput. Now, of course, as you see, this is in a closed court. It has only one controlled vehicle. And it's a completely different behavior with respect to what happens then also in real life in open road. And so we try to, starting from this experiment, we try to build up a theory to first reproduce what happened in this experiment and then try to see how we can expand further what happens in this experiment onto real world and open roads with more autonomous vehicles. So the first step here was to try and find how we could reproduce that traffic phenomenon that we see in there. So stop and go waves in particular in the circles, and also reproduce that typical control behavior that we see there. And so the first step for us was trying to understand what type of models to build this on. So the first step was using what is called microscopic model. So look at each one of the vehicle as its own set of systems of equations, and then try and connect them to each other, and then see if we could explain in a control system setting that behavior. And so the model that we built at first is a model that looks like the one you see here, which we call optimal velocity follow the leader model. So it has two parts. So the first is an equation that simply says that the derivative in time of the position of each vehicle I, it's equal to its speed. And the second part, which is the most interesting one, is the acceleration of each single vehicle. And that is separated in two sides. Let's say, so one side, which is what we call follow the leader. And so this first side here looks basically at the difference between the speeds of two consecutive vehicles and their relative distance. And so basically it says that when you're driving, you tend to relax your speed towards the speed of the car in front of you. And then we have a second part, which instead we call, it's the classical optimal velocity model that was introduced by Bando and others in the 1995. And here instead, the idea is that when you're driving, you not only tend to look at the distance with respect to the car ahead of you, but you also tend to relax your speed towards your optimal speed, so the speed at which you feel comfortable driving. And so this model here tends to kind of create a combination of these two aspects. So it looks from one side at how you can relax your speed towards what you're comfortable, and on the other side, relax the speed towards the leader. So this type of model here, if you want, it's possible to calibrate to reproduce the exact thing within on the experiment. So you're gonna see, you can see the creation of stop and go waves with this into circles. And
Maria Laura,
yes.
there is a question in the chat from Juan. Yes. Does the overall velocity decrease to the mean of the velocity? I think he was referring to the previous slide. You had not the...
Yeah, so if he's asking about the equilibrium, yes, the equilibrium will be the mean speed of the vehicles. Okay. Would be constant speed, actually, constant speed, yes.
Okay. Thank you.
Yeah. Oh, and thank you, and interrupt me because I cannot monitor the chat at the same time.
Yes, I will just find the right moment. I don't want to break the flow.
Sorry, yeah. Sorry, can I ask the question because I
got
a little
bit
confused. So you are showing the results with and without intervention. My question is, after the intervention, is the overall speed slower? I mean, I assume you leave like a slack of larger space between the vehicles and like the overall speed, because you show that the variance decreases. I mean, the mean of the overall speed between the two systems.
I don't recall we looked specifically at that, but we looked at the throughput, and the throughput increases. So even if we would have a lower speed, which may be possible, maybe not in all the experiment, maybe in some, but the throughput would still increase, throughput of the system. Okay, so starting from that model, we can reproduce what we've seen before, and then we can find basically what are the necessary sufficient criteria to have a stable system. And so this will depend obviously on your parameters. And so the parameters that you see here, for example, A and B, are the ones that can reproduce the stop and go waves. And then it will depend also on other things, among which it's the number of the vehicles that you will have in the circles. Obviously, this is a result that can be done in the linearized system. We have some results also on a nonlinear system, but I'm not going to show them here today. And then for the same type of model, we can also find out the string stability. So when we were looking at this experiment, we were thinking at the beginning if what is that actually causes the stop and go waves in a ring road? Is it asymptotic stability? It is string stability. And so we looked at different ways of producing the stability of the ring road, both in terms of string stability and otherwise in terms of asymptotic stability. And when we talk about stability, we need to talk about weak ring stability. And here you find the two conditions for which the system becomes stable. That said, this is still a theory that works for specific case, which is the case in which you have the ring road, and for which you have specific condition and specific 1 AV, so 5% of AV. In the ring road we've seen, we had 20 vehicles. And so how can we then move these results that we had in theory, that we have in application, to open roads and to more vehicles themselves? And so here it started for us what I find the most interesting thing, which is how can we actually expand what we've done in micro scale. So look at 20 vehicles plus 1 AV, in terms of theory and in terms of also experiments onto something that can be scalable onto open roads. And so we went back basically to the whiteboard and started thinking on how we see traffic flow models, right? And as we've seen, so there are different ways of doing traffic flow model. What we've seen before, it's microscopic models, but there are other ways in which people model traffic, and that depends on the different types of aggregation, what they want to describe, but also on the mathematical structure. So here, I'm going to show you two different ways of describing traffic. Again, they are not the only way to do it, they are the most common. And so there are two ways of doing it. So one is looking at macroscopic quantities in which we look at density, traffic density, average speed, and traffic flow. And its mathematical equivalent structure is a partial differential equation. Now, if you look at the partial differential equation here, that's a partial differential equation that comes from fluid dynamics. So it's the conservation of mass equation, also called continuity equation, that basically tells us that the evolution in time of the mean traffic density is given by the evolution, is equal to the evolution in space of the traffic flow. Basically, you can think of it, if you look at a road with only one entrance and one exit, the density, the change of density inside that road depends only on the current density and on the inflow and outflow. And so when we look at this type of model, then we'll have a solution that look like a density distribution. And when we talk about the flow is usually derived from experimental data. So here you have, for example, density versus flow. Each dot here is a measurement that you take, and then you can interpolate this data in different ways. So here it's an example, which is the green shield one. And the idea of the fundamental diagram is that you can separate your traffic flow into two sides. One side, which is free flow, the other side, which is congestion. This allows us to see traffic at a very high aggregated level. Then we've seen, when we looked at more at the very, if we look more into the details of the traffic, details of the couple driver car, then we might instead be interested in looking at headway, vehicle speed, vehicle acceleration, and then look at microscopic models like the one where we saw before, in which the mathematical structure will focus on its the classically ordinary differential equation, in which we have the derivative in time of the speed. It gives us some sort of acceleration function. And before we saw an example of an acceleration function, which was, for example, OVM, optimal velocity model plus follow the leader. And in this case, if you simulate, what you'll obtain is different vehicles trajectory. Now, as you can see, these two types of model, they describe traffic, but they describe traffic in a very different way. So in one way, we're going to look at very aggregated quantity. In the other way, we're going to focus on specific vehicles in the road. And you can think of that when you want to scale things up, the second approach, which is the macroscopic one, may be very computationally expensive, because imagine that you have at least two, if not three, sets of equations for each one of the pair driver cars that you have in the road. And so that means that you're going to have to calibrate your model to each one of the drivers in the road, and the model scales with the volume, so with the amounts of cars and drivers that you have on your road. The top model, which is the macroscopic model instead, is focuses more on aggregated quantity, and it scales with the links that you have on your network, because you're going to have one partial differential equation per link that you have on your network. Now, there's also another difference among these two models. So apart for the scalability, it also depends on the theory that we want to develop. For the microscopic model, we have a good handle on the mathematical theory behind the models, and especially the control theory. We are able, at least for what concerns traffic flow model, we are able to build, as we've seen also before, we're able to build models for which we can possibly build explicit and analytical control strategy, and also derive different sufficient and necessary conditions for controllability. For the macroscopic models, this is much more difficult, and up to now, to my knowledge, there's not a defined theory that allow us to design the analytical control strategy for macroscopic models. But, and why is that? Because if we look at macroscopic models, so specifically here, it's the nonlinear transport equation. In traffic flow literature is usually called LWR model that was introduced in the 50s. So the idea is that this equation here, it's nonlinear in the flux function, F, which is usually given the product between the traffic density and the traffic speed. And as I mentioned, this comes from usually experimental data. And even in the best case scenario, when you want to interpolate this with a bilinear function, which is the one you see here, still you don't have, it's hard to have explicit solution for this type of problem. In particular, the only type of solution that we are able to build for this model are what is called Riemann problem, which are building blocks of the solution of the LWR model. And so you have two types of solutions. So one, which we call shock wave, which is what also we have in traffic flow. That is when we go from low density to high density, basically when you're creating a queue. And the other solution, which is a rarefaction wave, which is the opposite, when we go from high density to low density. So you can think of a rarefaction wave when the queue is dissolving. So for example, if you are at a red light that turns green, you can think of shock waves, the type of solution that you would have when the waves is created. Now, that said, to deal with mixed autonomy, we would like something that scales, but we would like also to build some control strategy on the autonomous vehicle itself. And so we would like somehow to bridge those two scales that we have. And we would like to use a larger scale to describe the overall traffic dynamics, for example, using LWR, and that is something that has been proven to work quite well for traffic. And then we want to use maybe a micro scale to describe and control different vehicles that are, for example, automated vehicle or autonomous vehicles, for which we can build control strategy. And so what I'd like to talk to you about today, and also how that I would like also to show you some results on today, is how can we build a model that we called micro-macro model that allow us to describe basically the overall traffic dynamic with macroscopic behavior, and then instead describe the microscopic dynamic for AVs. And so the idea is that using this technique, we can use the microscopic scale to basically control and influence the overall traffic, but by doing control at the micro scale. And so using the AV, basically the AV at low penetration rate to control the overall traffic. And remember that our goal is to use then this to repeat what we saw in the ring road experiment in the overall road. So how does this work? So the idea is basically use the classical LWR to describe the whole traffic. And again, PDE, nonlinear PDE continuity equation. We don't need anything more complicated than that, at least for the moment. Then we want to describe each one of the vehicles that are controlled, for example, connected and automated vehicles with an ODE. So here, Y will represent the position of each one of the connected and automated vehicles. Y dot will be its speed, and then its speed will be found by the minimum of two terms. One, it's U, which will be our control. So in the uncontrolled case, it can be a constant speed. In the control case, we will find a way to find what is U. Or the other value that can also assume it's V, here, V of rho, which is the average traffic speed. Basically, this term here, it tells you that the AV can either go at the traffic speed or at a controlled speed. And lastly, we need a coupling term. So if we look just at the PDE plus the ODE, and you just simulate those two, basically it's the same as simulating a river flow with a grain of sand in it. So the AV will not have any effect onto the traffic because it will go with the traffic. So we need a way to find to connect those two scales. So this is done by this inequality constraint. So now this looks, by looking at it, it's hard to see its intuition. But the idea is the following. So imagine that this, instead of being an AV, it's like, for example, a truck, or for example, a bus. So what happens when you have those large and slow vehicles in the road? They are going to occupy part of the road, like, for example, one of the lanes. And the fact that they are there, that creates kind of a moving bottleneck, in the sense that they're going to occupy part of the road, reduce its capacity, and create basically a punctual reduction of capacity that goes along with this vehicle. And so the main idea of this control is exactly the same. So what you want to do is you would like to reduce the flow of the main traffic at the location of your controlled vehicle, and you want to reduce it by a certain factor, which we will call f of alpha. So how does it look like in the more specific case? So basically, you're going to have the OR road that follows, again, the main fundamental diagram. And so it's going to follow its highest capacity. And then you're going to have a smaller fundamental diagram that instead looks at the capacity in the reduced road. So in the road in the position which your AV is. So in particular, in this case, if you think of 3 lanes and your AV is in 1, then that reduced capacity is going to be 2 lanes out of 3. If the AV occupies 2 lanes out of 3, then it's going to be 1 lane out of 3. And how can we actually see this? Basically, you can think of the AV as a mobile obstacle. So the idea is that your AV is in the road and reduces part of its capacity. So here it's 2 lane, you have the CAV occupies 1 lane. Now, the other part is not only it occupies 1 lane, but it moves. And so this becomes a mobile obstacle. What does this mobile obstacle do? So basically, it changes the solution of our problem. And in particular, now, if we look at how our problem solution changes, so originally, I told you that the LWR has 2 types of solution, so rarefaction and shock wave. Well, once we have this type of mobile obstacle, the type of possible solution become 3. So, and what do they are? If the constraint is satisfied, the solution is still rarefaction and shocks. If the constraint is not satisfied, then we have a different solution. How does that different solution look like? And why do we have a different solution? So we started looking at this from first a perspective of, you try and reduce and eliminate all the difficult things. So first we looked at it as if it were a fixed obstacle. So this was done a few years back. And so if you look at a road with an obstacle, what are you going to see in it? So you're going to see a reduced capacity of the road. That reduced capacity is given by this point of your reduced fundamental diagram. That will be the F alpha that you have in your inequality constraint. And then that is going to basically define the density that you have upstream and downstream of your bottleneck. Okay? The same can be done when you have now moving spatial discontinuity. The idea is exactly the same. So you have that reduction of capacity. You want to find the upstream and downstream densities. So how do you do that? You look at the density before and after projected onto the higher fundamental diagram. Why now? So before you had a straight line. So why now you have this line here? Well, the idea is that your obstacle is moving, so that line basically becomes a line with a slope equivalent to the moving of your obstacle. And so now if we look at the solution, the idea is before we had, for example, a rarefaction. Now here you can see the constraint is not satisfied. And so now we have what we call a non-classical shock, which basically reproduce what we're trying to do with the bottleneck. So with the AV, we want to slow down traffic so that that slowdown will allow us to control the overall traffic. And we can prove existence, uniqueness of the solution for this model. We can prove that the solution is Lipschitz continuous with respect to the initial data. And which is what was more interesting for us was we can use several interacting CAVs. So now we are not stuck anymore to only one AV, but we can use this for how many AV do we want, and then we can construct basically the solution for different lanes, same lane interaction. But what is really important is that how does this look like? And so the idea is if you try and simulate this, now if you remember what I showed you at the beginning, now we're going to have the two scales mixed. So one scale is basically the density, and this is the density distribution at the bottom. So you have space versus time. And then we're going to have instead each single vehicle, which are the blue line here, that represents what the AV does. So here there's no control. So we were just playing around to show the different types of interaction that you can have with the different AVs. But so the important thing is that now we are able to have a density distribution. We're able to have an connect an automated vehicle with the density distribution, and we can show, and we can somehow influence the rest of the traffic with the CAV. Now, though, we still have not done any control so far. So far, we were just trying to model what we want to do on the open road, which is try and use a small penetration rate of AV to control the overall traffic. So how do we do control on it, and how do we do a control that is actually scalable and can actually be transferred to the real world application? So we started looking at this control problem. Again, we will start with the theory, and then we will see, we tried different approaches, and then we will see what type of approaches can actually be transferred and then scaled onto real life. So as I mentioned at the beginning, when we look at PDEs, there's different ways of doing control, and all of them have some advantages and disadvantages. And from a theoretical perspective, all of them have some advantages and disadvantages, and things that we can do and things that we cannot do. So the different things that we could do is, for example, we can do boundary control, which is access. We can do distributed control, we can do decentralized control, but what we actually wanted to look at for our own purpose is Lagrangian control, which is what we want to do. It's use, and that's why we built this micro-macro model. It's use some of the controlled vehicle to influence the flow of the macroscopic vehicles. And so we want to try and find a way for which we can have the CAV influence the flow of traffic. And so what does this translate to? So the idea is find the control U, where U is the speed of the AV, such that the solution of our problem, which is the density, will minimize a given cost functional. And this needs to be subject to our model. So H rho of U, it's the model, the PDE-ODE model you've seen before. Now, given the construction of the solution for the PDE, you cannot use gradient methods. And this is what makes this interesting from a theoretical perspective, a bit frustrating from a practical perspective when you have to do things in real life. So gradient methods cannot be applicable, and so we had to find ways to solve the problem without going through gradient methods. So as I mentioned before, analytical solutions difficult to find. We were able to prove some results on it, mostly the existence of a controller, specifically first in the open loop. So the open loop is the exact model you've seen before. Here, U, it's the controller of the AV, and you want to say that given certain initial condition, then your control U exists. That we can do. We can also prove that it has at least one optimal solution. And so here you can see, for example, if you have a bottleneck and you want to your CAV to basically slow down the traffic, it is possible to do so. And you can do it with 1 AV, 2 AV, and we can prove that this optimal control has at least one solution. But what is that solution? So how do we find the solution of this? And how do we scale this? So now we have in theory for 1 control, 2 AVs control to larger scale. Okay, so we started looking again at this type of problem. We used as a minimal, as a cost functional total fuel consumption. Why is that? Because again, we looked back at the stop and go waves. So we wanted to reduce stop and go waves. And one of the reasons why we wanted to reduce stop and go waves was to reduce the total fuel consumption of the vehicles. And we started to look at ways on how we could solve these problems. And so the first method we tried was model predictive control. And we tried up to 10 CAVs. So we can achieve up to 4%, almost 3.5 total fuel consumption reduction. And we can use controllers that are piecewise constant. However, with MPC, what is the problem with this type of problem is that it's hard to scale, right? So this is computationally, it's a bit expensive. So how do we scale if we want to actually go on open road and have more than 10 vehicles? And so we started looking also at different ways to maybe do model predictive control. So, and also other strategies. So do we want to do this as a centralized control? Do we want to do this as a decentralized control? Do we want to do this as a quasi-centralized control? And so we looked at all the different scenarios on how to do this. In all of them, we are able to reduce the total fuel consumption with respect to the baseline, which is with the case in which we don't have CAVs. But again, the problem of how to transfer then that into real life comes up, because if we want to, this is really computationally expensive, at least in the way we did it. And how do we transfer this to real world when you have more than 10 CAVs seem to be a greater problem. And so we started thinking about this from a different perspective. So far, everything I've told you was done through deterministic mathematicals and control theory methods. And so when we started instead looking, and then we wanted to apply this into real life, we started pivoting a bit from this problem here, from analytical solution to maybe something that will allow us to deploy this. And so we again went back to the blackboard, picked the same model, and then started looking at data-driven methods. And in particular, we looked at reinforcement learning. So how we build the theory now. Now, how can we build or find a control policy or an optimal control that allow us to bring this theory up to the real.
Maria Laura?
Yes.
Before going into this, there is a nice question from Umar in the chat, yes, asking, so in this model, the influence of a particular vehicle is basically restricting the traffic behind it with this term, with the minimization of UI and V. Can this model also allow you to influence cars to accelerate instead?
That's a great question. This model, no, but we have a different, I don't have it here, but we have a different model that is able to do exactly that. It's able to do the two things, both slow down and accelerate. And to do that, you have to change the ODE. So you have to change the vehicle's trajectory equation. You need to make there a term that allows you to accelerate. But in the specific models that you see here, it can only slow down traffic.
Okay, I see. Okay. Umar, if you have follow-up questions, just post them in the chat.
Yeah, that's very nice. Yeah, so probably also honking at cars in front to accelerate as well.
Yeah, exactly.
But
So
that would be difficult to model it.
That's the thing. You need to slow down traffic in a way that, and this we'll see in the real life experiment, and that's also where it comes up and will come up also in reinforcement learning. If you need to build a control strategy that will allow you to slow down, but not slow down too much with respect to what the other people are doing. Otherwise, you have very low compliance for the rest of the vehicles. So you can slow down, but not too much. Yes, so we started looking then how to apply this, and we looked at how to do this with reinforcement learning. So again, we take the same PDE-ODE model, and now we change the control strategy. So now that you see on the ODE, instead of creating it through classical control methods, we looked at reinforcement learning. And we looked at, so here we use the actor-critic methods. And we built basically the traffic problem as a Markov decision process in which the state space is your traffic density, the action space is the speed of the AV, so at which the AV will go. And then as a reward function, we used a combination of different factors. And so we have the traffic flow improvement, the speed optimization, and you had this last term, which is the total variation of the V. That goes a bit along what also Umar was hinting at. So you don't want a control speed that's changes a lot, and that changes a lot with respect to what the rest of the traffic is doing. Otherwise, it's not implementable. And so this is how, for example, the reinforcement learning policy looks like. So again, you see the density, you see the different stop and go waves, and then you're going to have your AV here. It's the red line, and you see when there is no control, the AV just follows whatever the traffic does, and then when there is instead control, the AV will start to slow down, so create a slowdown of traffic so that it's able to dissipate the stop and go waves. Again, this depends also on how you build your control. So here the goal was to dissipate stop and go waves, and so reduce in that sense also the total fuel consumption. And in this case, it will make sense to slow down so that you can actually dissipate the stop and go waves. If you have other types of functionals that you want like to control, the AV strategy may be different. So now we have something that can be scaled. So now how do we bring this into real life? And so this is something we did a couple of years back. So it's a joint project among 5 campuses in the US. So it's Berkeley with me, Professor Bayen and Jonathan Lee. Then there's Temple, Professor Seibold, Rutgers, Professor Piccoli, Vanderbilt, Professor Sprinkle, and Work, and an amazing group of PhD students and postdocs, which you all see here. And so the idea was to try and reproduce what we saw at the beginning in the ring road onto the open road, using low penetration rate and trying and using the models and the control strategy that we just saw there. And so again, the idea was to reduce dampen waves, and so reduce the energy consumption of traffic. How did we do this? So we had 100 plus vehicles. On each one of them, we mounted our own equipment and be able to control the vehicle themselves. We ran this on I-24 near Nashville, Tennessee for 5 days. You're gonna see the first day we ran stock ACC just to have a baseline. Day 2 was bad weather, so we didn't have any experiment, but day 3 and 4 and 5, we ran different controllers, and then we tried to see how the situation changed. Why did we go to Tennessee? Well, the idea is that there we were able to get this test bed, which is called I-24 motion that Professor Worker Sprinkle built up in Nashville. And the idea is that you have poles of high definition cameras that are around 500 feet from each other, and they allow you basically to reproduce, to see what traffic is there, and then you can extrapolate from the image that they have the time-space diagram, so each car's trajectory from the road. So how we built what we've seen so far into theory onto the cars. So we built for each one of the, for that stretch of freeway, from each one of the AV, what is called the mega controller. So the mega controller has two parts. One part, which is what we call the server side. So it takes data from INRIX, which is a data provider that gives us information about the average speed in segments of the freeway. And it takes also the ping from the different vehicles, so the position and the data of the vehicles, and then creates from this what is called a speed planning, which is what we've seen so far. So what is the best the best speed for the AV to basically reduce traffic in that stretch of freeway. Then that speed planner is going to be sent to the different vehicles, and the different vehicles will actuate to different types of controllers. So we're going to have the Nissan vehicles that are going to actuate basically ACC style of controllers. So they will actuate speed setting and gap setting. And then we'll have the Toyotas and the GM that instead will actuate acceleration type of controller, taking the speed planner as input on their lower level controller. So for the sake of time, and also for the sake of this talk, and also because that's the part that we actually actively in my lab work on, so we will focus on the speed planner part. So what does the speed planner do? It's exactly what we've seen before. So the idea is take the data that we have from real life, and so we have traffic data, which is INRIX, and then vehicle data ping. Use some techniques to predict the data and fuse it. So predict meaning each data, as you know, when you collect it, will have some lag. And so in order to do real-time controller, you need to somehow get rid of that lag. And this is what we do with the prediction module. Then fuse these two data sets, the traffic coming from INRIX and the vehicle pings. And this is to make sure that we get all the possible information that we have, and then design basically the target speed as we've seen before with the PDE-ODE model, and then send this to the microcontroller that then will do the low-level controller. So as I mentioned, we have two different types of data. One is INRIX that gives us an average speeds of segment. It has a very stable coverage. However, it has a 3-minute latency, which is not bad for this type of data, but for real-time controller, we need to get rid of the latency. And then the other one instead is the vehicle pings that tells us the observation of the vehicles and the car status. It updates basically every second, and so it's almost ignorable latency, but it has an unstable coverage. So it depends on the connection, and so sometimes you may not have all that information. So in order for us to do a controller that actually makes sense, we need to kind of unify these two data sets. So in a way, we need first to compensate for the time latency and then fuse those two data together so that we can have what we call an enhanced traffic state estimation. And so here you see, for example, how the two looks like. So this is what INRIX will give us, and this is what we will estimate beforehand to get a 3 minutes ahead prediction. So now we have the input of the controller. So now we are here basically in the server side controller. How do we build the speed planner? But the idea is exactly what we've seen so far. So basically, what do? You take your PDE-ODE model, Offline, we train it with an RL policy, like similar to the one that we have, and that will give us a speed. The same we will do in real life. So you take your real world data, take the RL policy that we trained offline, and then use that policy to, once we have it informed with the real data set, to get basically the information, the U, through the vehicle themselves. And this is an example of how it looks like. So in blue, the solid line blue, it's the INRIX data. The green line is the predicted INRIX, which is what we try to predict to reduce the latency. And then we have the target speed, which is what our AV produces. And the dots here are the pings. So as you can see, you are slowing down the vehicles, but you are just preventing them to slow down before they actually hit the queue. And so the idea here is how you see the speed planner basically works. This is in a simulator. So you're gonna see basically this is your congestion, your queue, your bottleneck. And so what you're trying to do is to create basically this buffer so that people, they don't arrive at the worst queue possible, but they have a kind of buffer before they end up at the end of the queue. And this information is then spread down to the low-level controller that then, based on the observation, it's able to design the decide speed for each single AV. And so in practice, how does it work? So what the people do, the people that are into the cars, all they have to do is turn on the ACC, and then we will take over and control of the car that will set up basically a speed and gap setting between the two cars. And so here in the morning of the experiments, this is how it will work. So the cars will go, during the night, we will update the controllers. The cars will go down into the freeway, and then at some point you're gonna see this is gonna be overlaid with the pings of the cars that go onto the freeway, and you can see the ACC set speed. So what the controllers basically told the cars to do. So here it's where we had the headquarters, and then you'll see them slowly moving onto the freeway. So two things. First one is, how does the traffic look like normally in that stretch of freeway? Normal traffic there looks like this. So here you have, this is space-time diagram. These are car trajectories, color-coded based on speed. Red means congestion, green means free flow. This is without any type of control, and you can clearly see stop and go waves, right? So you can see this behavior of oscillatory traffic. Now, if you overlay this with 100 vehicles, you know what they do? The 100 vehicles basically become an overlay on this. This is the Monday when we had just stock SEC. And the idea here is that those stock SEC just do less than, or that AV have only 2% penetration rate with respect of the rest of the overall traffic. So what can you actually do with 2% penetration rate? So we looked at the different bottlenecks. So we looked at the different congestions. We do this in simulation, but also on the field test. So you have different controls. So again, Monday and Tuesday, we had no control because here we had stock SEC, and this we didn't run any controller. And we kind of used Monday as a benchmark for that reason. And then you can see that when we use all the 100 AVs, so we had an average density that decreased, and we decreased the average density ahead of the bottleneck, so upstream of the bottleneck and downstream. And the congestion density, the congestion of the bottleneck gets also reduced. Obviously, this is done with 2%. So I expect that as the number of AV and the valid penetration rate increases, you'll be able to get even better results on this. So these are all the support that we had throughout the experiments, both for the analytical part and for the more applied part that you've seen at the end. Big thank you for all the people that participated in this. So here you can see my postdocs and my students and all the other postdocs and students that participated. And this is a list of papers that came out or that were referenced throughout the talk, and I'll stop here. Thank you very much.
Thank you so much, Maria Laura. And Joel has to left earlier for PI meeting, and he asked me to host the Q&A session. And there's a question in the chat saying that, is this stretch of the highway flat? I would imagine that waves could be more likely to appear on climbing stretches.
It's not completely flat, and also right before the end of the free. I don't know if I don't have a plot here, but so right before the end of the freeway, there's a hill before our stretch of freeway. So here it's flat where we did the experiment, but right here it starts to the climb up. So that comes back to our stretch, to our side of freeway.
Okay, thank you for your answer. And are there any other questions in the chat and or also just
I do have some questions if there is room for questions still.
Yeah.
Can you hear me?
Yes.
Hi, Maria. Good to see you again. I think we met like 2 years ago
Yes.
at FPSC.
Nice.
Good to see you. Thank you very much for the nice presentation. I really enjoyed it. I have several questions. Just to start with the first one. So it is really interesting to see, like from an efficiency point of view, that although one vehicle itself might be not so efficient, if you want to say like compared to a human, it's not as fast as a human can be, but it can have some effects on the system and make it improve. But did you also explore that in the simulation to see what would be the spot point, the sweetest spot for the system that at this level of penetration rate, we will see like the best results from this harmonization?
That's a good question. So obviously the penetration, so as the penetration rate grows, you have better controllability of the system. What we've seen is that so at least in penetration in simulation, around 10 to 20%, you're gonna have already start having very good results. Anything below 10%, it's very hard to control the system. And then above that, obviously, you increase the controllability, but you need at the very least 10%. But we don't have, we never done explicit results on it, so I don't have like a plot that can show this. But
thank you. And maybe next question, then I'll give room to others. Did you see any issues with training the reinforcement learning in the simulation and then bring it to the real world, like the gap between the simulation and real world?
We had, and we had both for the speed planner and for the local controller. So the local controller also, some of them, especially for the Nissan, are RL based. And once we actually put it in the hardware, then we realized that we had to do blind, like we were not able to get into the exact inputs that we wanted for the RL controller in the car, and so we had to basically rework our RL algorithm on the last days to make sure it would run in the car.
Okay.
Yes.
Interesting.
Yes.
Thank you.
And also there's a question in the chat about could the future of 100% autonomous vehicle on the highway significantly improve traffic flow? Would there be any energy efficiency parity with other mediums of transportation like trains or buses?
Oh, that's a good one. So it will improve. It depends on what are your metrics. For sure, like if you have 100% penetration rate, then you have complete controllability of your system in a way, assuming that you can have the cars do what you want. Like it's then at least from a traffic perspective, that probably would help. From a energy efficiency part, it depends on what is your fleet, and if it's better than train and buses. Well, my answer here would be always that transit is always bad. Like, if you want to reduce, if you do the equivalency, one AV, one car nowadays, if there is too many cars in the road, there are going to be too many cars in the future. The AV is not going to help us with that. So we need to find a way to have higher occupancy vehicles in the road. And so in that case, I think transit would be better. But from energy perspective, it will depend on what type of fleet we have. So if it's an electric vehicle, ICE vehicle, or what type of vehicle will have.
Okay, thank you for the answer. And any other questions? Okay, so thank you very much, Maria Laura, for giving such a great talk. And yeah, thank you again. It's very good, very impressive. Yeah, thank you.
Thank you for having me. Thank you.
Thank you.